You know, have you ever really thought about what it means for a line to be unbroken? It sounds pretty simple, right? But in the world of math, proving something is perfectly seamless, well, that takes a little bit of detective work. So today, we're going to put on our detective hats and crack the case of continuity.
I mean, we all get the basic idea. An unbroken line is one you can draw without ever lifting your pen from the paper. But what if there's a tiny, microscopic point missing? Or what if the line suddenly jumps from one spot to another? How can we be absolutely sure it's connected? That's the big mystery we're diving into today.
So I want you to think of yourself as a continuity detective. Our whole mission is to look at any path, what mathematicians call a function, and figure out with total certainty if it's truly continuous. This isn't just about looking at a picture, it's about proving it.
Okay, so let's get into the first part of our investigation. We're going to go from just having a gut feeling about what an unbroken line is to having a hardcore, rigorous method for putting any line to the test.
Our eyes can totally be tricked, especially when you get into really complex graphs. To be a good detective, you can't just rely on what you see. We need a system, a reliable test that's going to work every single time for every single point we want to investigate.
So here it is. This isn't just some boring list of rules from a textbook. No way. This is the official toolkit for the continuity detective. It's a simple, three-step test that lets us interrogate any point on a function and find out the truth about it.
And honestly, it's a really powerful process. First, we ask, is there even a point there? Like, if you go to a specific spot, does the function actually give you a value? Second, as you get closer and closer to that spot from both sides, are you heading toward the exact same location? And third, the final check. Does the spot you are heading towards actually match the point that's really there? A function has to pass all three of these tests, no exceptions, to be called continuous at that point.
All right, we've got our toolkit. Now it's time to actually use it. Let's open up a couple of case files and see this three-step test in action. Time to get our hands dirty.
Okay, here's our first suspect. We're looking at this function, and we're zoning in on one specific point, where x equals 2. So let's apply our test. Step 1. Does the point even exist right there at x equals 2? And boom, we stopped it on the very first step. When we try to plug 2 into that function, we end up with 0 divided by 0. That's a huge red flag in math. It's undefined. It means there is literally no point on the graph at x equals 2. Case closed. This function is discontinuous.
All right, let's move on to our next case. This one's a little more clever. It's a piecewise function, which is just a fancy way of saying it plays by different rules depending on where you are. Our investigation is focused right on that spot where the rules change, at x equals 3.
Okay, let's run the test. First up, does a point exist at x equals 3? Well, if we look at the rules, that top rule says it applies when x is less than or equal to 3. So we plug in 3 and we get an answer, -5. You can see it on the graph, it's that solid dot. So it passes step 1. Now for the real question, does the limit exist?
And this is where the whole thing falls apart. It's brilliant. If you follow the path from the left side, you're clearly heading towards a value of -5. But if you come at it from the right side, you're heading somewhere completely different, a value of +4. Since the two paths don't meet up, the limit doesn't exist. It fails test number 2. Another case of discontinuity solved.
So now that we know how to spot a break, let's start categorizing them. You see, every time a function fails our test, it creates a specific type of break. It's time to look at the official rogues gallery.
And here they are, the three main ways a function can be broken. Our first case, that was a hole, what we call a removable discontinuity. Our second case was a classic jump. And that third type is an infinite one, where the path just flies off the chart into, well, infinity.
The first one, removable, is kind of like a bridge with just one plank missing. You could easily fix it by just defining that one missing point. A jump is where the two sides of the bridge don't line up at all. And an infinite discontinuity, that's like a path that leads right to the edge of a bottomless canyon.
So we've learned how to find breaks and how to classify them. But this isn't just some abstract math exercise. All this detective work, it unlocks an incredibly powerful tool. It gives us a guarantee. And this, right here, is the payoff. So what is this big reward for all our hard work? What's the point? It's a guarantee, a promise that is only possible for paths that we can prove, without a doubt, are unbroken. And here it is. This is that guarantee. It's called the intermediate value theorem. I know, it sounds super technical, but the idea behind it is stunningly simple. And here's the kicker. It only works if the function is continuous.
This picture explains it perfectly. If you are walking on a continuous mountain path from a low point to a high point, you can't just magically teleport. You are absolutely guaranteed to pass through every single elevation in between. Continuity is the key that makes this promise unbreakable.
So let's use our powerful new tool to crack one last big case. We need to prove that this function, x minus cosine of x, has a 0. All that means is that it has to cross the x-axis somewhere. We don't even need to find out where, we just have to prove that it happens.
Okay, first, we confirm our function is continuous, and it is. Now we just need to set up a start and an end point for our little hike. Let's start at x equals 0. At that point, the function's value is -1, so we're below sea level. Then, let's check our end point at x equals pi over 2. Here, the value is positive. We're now above sea level.
And that's it. That's the whole proof right there. The final verdict. Since we know the function is continuous, and we know it goes from a negative value to a positive value, the intermediate value theorem guarantees that it absolutely must have crossed 0 somewhere in between. We've proven a solution exists without even finding it. That is the real power of continuity.
So in the end, continuity gives us certainty. It's a mathematical promise. It guarantees that between any 2 points on an unbroken journey, every single value in between has to be visited. Just think about it. The growth of a plant, the change in temperature, the value of a stock. If those paths are continuous, what other powerful guarantees might be hiding there, just waiting for a good detective to come along and uncover them?